So you want to discover a new particle. Great, but where do you start? Well, you might want to take a few tips from physicists at CERN in Switzerland, the European Centre for Research on a Subatomic Scale, and the place of discovery of the infamous Higgs Boson, often referred to as the God particle, but that's a bit of an exaggeration. The thousands of scientists at CERN conduct their research using some of the most advanced scientific equipment in the world, which all centres around the LHC, or Large Hadron Collider. The LHC is a 27-kilometre long particle accelerator, an underground circular machine that uses magnetic and electric fields to spin two identical particle beams around at about 1 billion kilometers per hour in opposite directions. Eventually, these beams are smashed together at enormous energies. The job of researchers at CERN is to analyse the stuff that comes out of these collisions. So why is this so interesting? The particles that are collided are protons, the positively charged particles in an atomic nucleus. So you might expect a collision between individual protons from each beam to result in the two protons bouncing off each other and going their separate ways. But theories developed by Albert Einstein explain why the reality is very different. Einstein's famous equation, E equals mc squared, gives us the concept of mass-energy equivalence. Mass is just a form of energy. The two are interchangeable. The consequences of this are huge. The faster protons move, the more energy they possess, and so, by virtue of mass-energy equivalence, the more mass they can be considered to have. So, when individual protons collide, this newly acquired mass energy can't just disappear, it has to go somewhere. And it goes into the formation of a whole bunch of different particles completely different from the beam of protons we started with. So the whole of the Large Hadron Collider is basically a way to convert huge amounts of energy into tiny subatomic particles. Now, some of these particles, like the Higgs Boson for example, are very unstable. They only exist for a fraction of a second, then they decompose almost instantly into a variety of different fundamental particles. This short existence explains why we haven't been able to detect these particles before, but also makes it pretty difficult to go about finding anything new. This doesn't faze researchers though. Located around the collider are 4 detectors that can take measurements of the fundamental particles that are produced from the millions of collisions every second. Analysing the amounts of each kind of particle produced tells us what's going on inside the collider. So, if we detect an unusually large amount of particles that we would expect to come from a particle like the Higgs decomposing, and we see this consistently over a long period of time, this can be used to prove the existence of the particle. So really, when you go about finding a new particle, you never actually see the particle itself, only evidence that it was there for a tiny portion of time. But nature isn't inclined to make things easy.